Now let's move on to the next topic of our chapter, subsets. Let us understand this concept with the help of an example. Consider a school. Let us represent the students of class 11 of that school as a set. Let it be set A. Now consider another set, the set of all the students of that school. Let it be set B. Now, how can we relate these two sets? We can say that every element of set A is an element of set B. How? Because every student of class 11 is also the student of that same school. This is where the concept of subset kicks in, and we can say that set A is the subset of set B, and symbolically can be represented like this, where the symbol stands for is a subset of. So how can we define a subset? We can say a set A is said to be a subset of set B if every element of A is also an element of B, which can mathematically be represented using symbols like this, where A represents elements and this symbol means implies and can be read as A is a subset of B if A is an element of A implies that A is also an element of B, and if A is not a subset of B, then we can write it like this. So for A to be a subset of B, the only condition is every element of A has to be in B. But it's not necessary that every element of B is also in A. But in case if every element of B is also in A, then B is a subset of A. So in this case, both A and B are the same sets, and we can write A is a subset of B and B is a subset of A if and only if A is equal to B. Here, this symbol denotes two-way implications and is read as if and only if. Now, let's take a look at some examples for better understanding. Here are two sets A and B. A equal to set of 5, 2, 7 and B equal to set of 2, 8, 5, 6, 7 and 9. From looking at these two sets, can you tell me if one set is the subset of the other? We can see that every element of A is an element in B, but every element of B is not an element of A. So we can say A is a subset of B. Let's look at another pair of sets. A is equal to 4 and 9 and B is equal to 5, 8 and 2. As you can see, neither of the sets have all of their elements in the opposite set. So we can write A is not a subset of B or B is not a subset of A. Now let's take a look at another pair of sets. A is equal to set of 2, 5 and 8 and B is equal to 5, 8 and 2. Here both the sets have the exact same elements, which means that every element of A is also in B and every element of B is also in A, and we can write A is a subset of B and B is a subset of A if and only if A is equal to B. Now, in the first example, every element of set A is in B, but every element of set B is not in A. So, A is a subset of B and A is not equal to B. So, if A is a subset of B and A not equal to B, then A is called proper subset of B and B is called superset of A. There are two rules when it comes to subsets. First one, take any set A, then every set A is a subset of itself. For example, if A is equal to set of 1, 2 and 3, then A is a subset of A. The next rule is an empty set is a subset of every set. Let's move on to the next topic, Singleton set. As the name indicates, a set with only one element is called Singleton set. For example, A equal to set 2 is a Singleton set. B equal to set 0 is a Singleton set, as 0 is also an element. C equal to set of set 3, 4 is also a Singleton set. As you can see, set 3, 4 is a set itself and has two elements, 3 and 4. Then how can it be a Singleton set? We can also see that set 3, 4 is again included in braces, which makes it a single element. Hence, C is a Singleton set. Now let's take a look at some examples for better understanding. First one, consider the sets phi A equal to set 1 and 3, B equal to set 1, 5 and 9, C equal to set 1, 3, 5, 7 and 9. Insert the symbols subset or not a subset between each of the following pair of sets. Here is the first one. We know that an empty set is a subset of every set. So we can write phi is a subset of B. Here is the next one. As you can see, every element in A is not in B. 3 belongs to A, but 3 does not belong to B. So we can say that A is not a subset of B. Here is the third one. We can see that every element in A is an element in C. So we can write A is a subset of C. Here is the last one. We can see that every element in B is an element in C. So we can write B is a subset of C. Now let's move on to the next example. Let A equal to set A, E, I, O and U, and B is equal to set A, B, C and D. The first question is A a subset of B? It's clearly not, because we can see that every element in A is not an element in B. The elements E, I, O and U are not present in B. So we can say that A is not a subset of B. The second question is B a subset of A? Similar to the first question, we can see that every element in B is not an element in A. So we can say that B is not a subset of A. Now let's move on to the next example. Let A, B and C be three sets. If A belongs to B and B is a subset of C, is it true that A is not a subset of C? If not, give an example. Let us consider an example here. Let A equal to set 1. It's given that A belongs to B. So the entire set A will be an element in set B. So let's make another set B according to that condition. B equal to set of set 1, 2 and 3. So let this be our set B. It's also given that B is a subset of C. Next, let's write a set C according to this condition. Let it be C equal to set of set 1, 2, 3, 4 and 5. So here A belongs to B, as set A is an element in set B, and also B is a subset of C, as C contains all the elements of B. But the question here is if A is a subset of C. For A to be a subset of C, the element 1 must also be in C. That is, 1 belongs to A and 1 belongs to C. But that's not the case in set C. In set C, the element is set 1 and not 1. That is, Set 1 belongs to C, but 1 does not belong to C. So we can say that A is not a subset of C. Now let's move on to the next topic, subsets of set of real numbers. In this topic, we are going to take a look at the various subsets of real numbers. We know that real numbers include positive and negative integers, rational and irrational numbers. We have already come across a few sets earlier in this chapter. Next one is the set of all rational numbers. We know that a rational number is a number that can be represented as the quotient p by q of two integers such that q not equal to 0. In set builder form, it can be written as q is equal to set of all x such that x is equal to p by q, where p and q belongs to the set of integers and q not equal to 0. Some examples of rational numbers are 3 by 8, 3, because 3 can also be written in the form p by q. Can you tell me how? Yes, 3 can also be written as 3 by 1, which is of the form p by q. Next one is 10 by 3, which is equal to 3.333, etc. As you can see, this is a recurring decimal, where the decimal number repeats forever. And recurring decimals are also rational numbers. Next one is mixed fraction 3 1 by 2, which is also a rational number, as it can be written in the form of p by q. That is 3 into 2 plus 1 by 2, which is equal to 7 by 2, and that is a rational number. Next one is the set of irrational numbers. We know that an irrational number is a number that cannot be expressed in the form of p by q. That is, all real numbers that are not rational numbers. And in set builder form, they can be written as t is equal to set of all x such that x belongs to the set of real numbers and x does not belong to the set of rational numbers. For example, root 2, root 5, pi, etc. They cannot be written in the form of p by q, and if we consider their values, we can see that they are non-terminating and non-repeating decimals. Such decimals are irrational numbers. Now, let us compare these four sets: the set of all natural numbers n, the set of all integers z, the set of all rational numbers q, and the set of all irrational numbers t. On comparing them, we can see that n is a subset of z, as each element of n is also in z. Now, rational numbers are made up of positive and negative integers. So we can say that z is a subset of q. We know that real numbers include both the rational and irrational numbers. So we can write q is a subset of r. And since the rest of the subsets are not related with irrational numbers, we have to write it separately. That is, t is a subset of r. Therefore, n, z, q, and t are the subsets of the set of all real numbers r. Our next topic is intervals as subset of real numbers. An interval is a set that consists of all real numbers between a given pair of numbers. Generally, there are two types of intervals: open interval and closed interval. And there is also a third one, that is interval closed at one end and open at the other end. First, let us take a look at the open interval. Let a and b belong to the set of all real numbers and a less than b. Then open interval a comma b is equal to set of all y such that a less than y less than b. Let me explain this to you in detail. Here, a and b belong to the set of all real numbers and a is less than b. And the condition given here is a is less than y and y is less than b, where a and b are the endpoints and y represents all the elements that lie between a and b. A thing to be noted here is, since y is greater than a and less than b, the endpoints a and b will not be included in the interval, and we can denote the open interval by writing a, b inside open brackets. Let's take a look at an example for better understanding of this concept. Now, let's take a look at an example for better understanding. Consider the set of all x such that x belongs to the set of all real numbers and -2 less than x and x less than 4. So how can we write this set in interval form? Let's take a look. As you can see, the condition given here is x is greater than -2 and x is less than 4. So this set represents the elements that lie between -2 and 4. Now, if we represent this set on the number line, we can see the two endpoints -2 and 4. Since x is greater than -2 and less than 4, these endpoints are not included, which makes this an open interval. So, in this interval, all real numbers that lie between -2 and 4 are included. The endpoints -2 and 4 are not included, and we can write this interval as -2, 4 inside open brackets. Now let's take a look at the next type, that is closed interval. Let a and b belong to the set of all real numbers and a is less than b. Then closed interval a, b is equal to set of all y such that a is less than or equal to y, y is less than or equal to b. The only difference between open and closed interval is, in closed interval, the endpoints are also included. Let us take a look. Here, a and b are two elements that belong to the set of all real numbers, and a is less than b. And the condition given here is a is less than or equal to y and y is less than or equal to b, where a and b are the endpoints and y denotes the elements that lie between a and b. A thing to be noted here is, since y is greater than or equal to a and less than or equal to b, the endpoints a and b will also be included in the interval, and we can denote the closed interval by writing a, b inside square brackets. Now, let's take a look at an example. Consider the previous example with slight change, that is, set of all x such that x belongs to the set of all real numbers and -2 less than or equal to x and x less than or equal to 4. So how can we write this set in interval form? We can see that the condition given here is x is greater than or equal to -2 and less than or equal to 4. So this set represents the elements that lie between -2 and 4. Now, if we represent this set on the number line, we can see the two endpoints -2 and 4. Since x is greater than or equal to -2 and less than or equal to 4, the endpoints will also be included, which shows that this is a closed interval. So, in this interval, all real numbers that lie between -2 and 4 are included. The endpoints -2 and 4 are also included. And we can write this interval as -2, 4 inside square brackets. Now, let's move on to the next type of interval, that is, interval closed at one end and open at the other end. There are two types in this form. First one is open interval from A to B including A but excluding B. Second one is open interval from A to B including B but excluding A. Let's take a look at the first one. Open interval from A to B including A but excluding B. Let A and B belong to the set of all real numbers and A less than B. Then open interval from A to B including A but excluding B is equal to set of all y such that A less than or equal to y and y less than B. As you can see, the condition given here is y is greater than or equal to A and less than B. So what are the endpoints here? They are A and B, and according to the condition given, A is included in the interval and B is not included in the interval. Let's take a look at an example. Consider the set of all x such that x belongs to the set of all real numbers and 3 less than or equal to x and x less than 5. Here the condition given is x is greater than or equal to 3 and less than 5. So if we represent this set on the number line, we can see the two endpoints 3 and 5, and according to the condition given, 3 is included in the interval and 5 is not included in the interval. So this interval consists of all real numbers that lie between 3 and 5. But here the endpoint 5 is not included, and we can write this interval as 3, 5 enclosed in a square bracket and an open bracket. Now let us take a look at the second one. Open interval from A to B including B but excluding A. Let A and B belong to the set of all real numbers and A less than B. Then open interval from A to B including B but excluding A is equal to set of all y such that A less than y and y less than or equal to B. As you can see, the condition given here is y is greater than A and less than or equal to B. So what are the endpoints here? They are A and B, and according to the condition given, A is not included in the interval but B is included in the interval. Let us understand this with the help of an example. Consider the set of all x such that x belongs to the set of all real numbers and 3 less than x and x less than or equal to 5. Here the condition given is x is greater than 3 and less than or equal to 5. Now if we represent this on the number line, we can see the two endpoints 3 and 5, and according to the condition given, 3 is not included in the interval and 5 is included in the interval. So this interval consists of all real numbers that lie between 3 and 5, but here the endpoint 3 is not included, and we can write this interval as 3, 5 enclosed in an open bracket and a square bracket. We can easily find length of an interval by subtracting A from B, that is B minus A, and this can be done for any kind of interval. Now let's move on to the next topic, that is power set. Let us consider a set A is equal to set of 1, 2. So can you tell me what are the subsets of this set? We know that phi is a subset of every set. So we can say phi is a subset of set A. Now each element can also form a subset of the set. Here the elements are 1 and 2. So we can say that set 1 and set 2 are the subsets of set A. Also, we know that every set is a subset of itself. So set 1, 2 is a subset of the set A. So there are 4 subsets in total, and they are 5, set 1, set 2 and set 1, 2. Now let us form a set with all these subsets. So this is a set of all the subsets of the set A, and this set is called the power set of set A. So how can we define the power set? The collection of all subsets of a set A is called the power set of A, and it is denoted by P of A. In P of A, every element is a set. So for the set A is equal to set 1, 2, P of A is equal to set of 5, set 1, set 2 and set 1, 2. Also, the number of subsets or elements in a power set can be found out by using the formula n of P of A is equal to 2 raised to m, where m is equal to n of A, that is number of elements in the set A. So here set A has 2 elements, then the number of elements in the power set A is equal to 2 square, which is equal to 4. Our next topic is the universal set. The basic set, which consists of all elements of subsets, is called the universal set. The universal set is denoted by capital U, and the subsets are denoted by capital letters A, B, C, D, etc. Let us take a look at an example. Consider two sets. A is equal to set 2, 3 and B is equal to set 1, 3 and 5. Then the universal set will be set of 1, 2, 3 and 5. We can see that the universal set consists of all the elements of subsets. Here A and B are the subsets of the universal set. Another example is the set of all real numbers is the universal set for the set of all natural numbers, the set of all integers and the set of all rational numbers.